Um, this lab is a continuation of Lab 1, where we calculated the charge on a piece of tape to be 7.8 nanocoulombs and verified this value with a simplified computational model. In this lab, we use a more complex computational model to try to verify the value determined in Lab 1. And this computational model ended up not corroborating that value. We use Coulomb's law to calculate the charge on each piece of tape. Coulomb's law gives us this equation, which can be rearranged into this form to solve for Q, given F, R, and K. The R is the distance between the two pieces of tape, which can be measured with a ruler, and F can be determined with a free body diagram. Where levitating a piece of tape, we know that the net acceleration on the tape is 0, meaning the net force on the tape must be 0, meaning the electrostatic force must be equal in magnitude to but opposite in direction to the gravitational force, which we can calculate using F equals mass times acceleration due to gravity. For the Lab 1 experiment, we charged each piece of tape by stripping it off another piece of tape. When held next to a negatively charged pen, these pieces of tape were attracted to it, indicating that they were positively charged. We then suspended one piece of tape and then levitated it by moving a second piece of tape underneath it. By measuring the distance in between the two pieces, when the first tape started levitating, we could obtain a value R to plug into the equation. We measured R to be 19 millimeters. We calculated the gravitational force on the top piece of tape by finding its mass and multiplying it by acceleration due to gravity, which we calculated to be 0.00153 newtons. Plugging that value into the equation, we calculated the charge to be 7.8 nanocoulombs, and this value was corroborated by a simplified computational model where each piece of tape was represented by a point charge. Inputting the charge value resulted in two force vectors of opposite magnitude but equal direction. In their more complex computational model, we simulated each piece of tape as a line of 30 point charges, and then plugging in the mass, distance, and charge of each piece of tape, the program would calculate the force on the top piece of tape. And plugging in our charge calculated in Lab 1 resulted in two unequal force vectors. The gravitational force is much greater than the electrostatic force, indicating that our value in Lab 1 was not correct. We calculated this force for each point charge in the top tape. We iterated through each point charge in the bottom tape and calculated the E field on that top charge by that bottom charge, and then summed each of those contributions together to get the net E field on that charge, which we then used to calculate the net force on that charge, and summing all those forces on each of the top charges together resulted in the net force on the net electrostatic force on the top piece of tape. Possible sources of error: air resistance and tension in the tape would have made it harder for the electrostatic force to move the top tape, and any values inputted into the programs were rounded to 3 decimal points. The charge calculated in the experiment was 7.8 nanocoulombs, but the charge resulting in 0 net force in the computational model was 1.915 times 10 to the negative 8th coulombs, meaning the assumption we used treating our tapes as point charges in Lab 1 resulted in an underestimate of the charge needed to levitate the tape. These estimates differ because when simulated as a point charge, the charges are on average closer together. The computational model is more likely to be accurate because the charges are arranged on a line, which is closer to how they're arranged in real life. In conclusion, we demonstrated how charged objects interact and attempted to calculate the charge on a piece of tape, which we determined to be 7.8 nanocoulombs, but this value was not corroborated by the complex computational model, indicating that our decision to treat the tape as a point charge in Lab 1 resulted in error.